Okay, welcome back to part 3 of SPSS 2. We're talking about the null hypothesis and how we evaluate this. And so this is a process that we would go through each time that we would want to actually uh, do some sort of analysis. And so really in some cases or actually in most cases, we're going to want to reject the null hypothesis and consider the alternative hypothesis. So we're going to want to take that straw man and knock him down and say, well, we don't really have the data to suggest that that's a reasonable explanation for the way things are. And so we want to then possibly accept that alternative hypothesis. Now, as a researcher, one of the things that you need to do prior to your study is to establish an alpha level. Now, alpha is defined as the probability of rejecting a null hypothesis when it is actually true. So in other words, you would say that the null hypothesis, I don't believe is true, but in the real world it actually is true. So you can decide what that probability might be prior to your experiment. And most typically in most educational and psychological settings, researchers will, by sort of standard approach, set that alpha level equal to 0.05. And Yaki, in his text, he uses 0.05 in really all of his examples. However, you should know that that is not set in stone, and that the researcher has some evidence to use a different alpha, then he or she could actually change what the alpha level is, of course, giving some sort of explanation why they had chosen that particular level. So let's say you decide on the outset of your experiment that you want to use an alpha level of 0.01 rather than 0.05. Oh, sorry, 0.01 to 0.05. That is a more stringent requirement. So the likelihood of you rejecting the null hypothesis when it's actually true would be reduced. And so that would produce a case where you're less likely to reject the null hypothesis. On the other hand, if you wanted to be a little bit more liberal and give yourself a sort of a wider range of possibilities, you could set your alpha level to 0.10. And in fact, a lot of people do, because the effect sizes in psychological and educational studies typically are fairly small. So setting a more liberal alpha value to 0.10 is going to provide a situation where you're going to be more likely to reject the null hypothesis. So really, by convention, people will pick 0.05. There's really no reason why it has to be 0.05. That's just traditionally the way things are, and the way things that Fisher set things up way back in the 1930s, because they didn't have computers back then and they had to look things up in a table. So they built two tables of numbers, one of 0.05 and another one of 0.01. But since we have SPSS, we really don't have to kowtow to those set in stone sort of values. So there's nothing special about them, but by convention, we pick 0.05. So on the outset of your study, you'll need to decide what that is and communicate that to the reader of your study. So also, when you evaluate the null hypothesis and you get your output from SPSS, you're going to get a p-value. And P is the probability of attaining the sample that you got if the null hypothesis is true. Okay, so if there is no differences between the groups, then the chances that you would get that particular data set is illustrated by P. And so here written out in the sort of formal logic way of looking at things. So we can see here that P, the probability of getting your data based on the assumption that your null hypothesis is correct. So that's what P is telling you. Now, when you get your results in SPSS, it's not going to say P, but in the table, it's going to have the words SIG, S-I-G. All right, and so it's going to be kind of weird because you just sort of need to learn that the p-value that's coming out is whatever's in that column that says SIG. So let's take a look at how we would ask the questions and answer the questions if we were performing our statistical analysis. And so we've gone ahead and we've run in SPSS the analysis that we were running. Let's say it's an independent samples t-test. And if our p-value is less than or equal to the alpha that we set out at the beginning of our study, and again, in most cases, that's 0.05, then we would reject the null hypothesis and we would assume the alternative hypothesis. Okay, so that's if our p-value is less than that alpha we set. Apologize for Lucy the Labrador there. She has a little bit different opinion about statistics than I do, but nonetheless, so back to where we were. So if the p-value is less than or equal to alpha, then we're going to reject our null and assume the alternative. And again, to just kind of contextualize this, this is kind of what we usually want to do. On the other hand, if our p-value is greater than alpha, then we do not reject the null hypothesis, and then we assume that no differences exist. So we would assume that our null hypothesis is the correct interpretation. But we never say that the null hypothesis is correct, but instead we say we do not reject the null. So there's really only two outcomes to this null hypothesis significance testing. Either you reject the null or you do not reject the null. And if you reject the null, you can then assume your alternative hypothesis. But if you do not reject the null, that's just the way that you report it. So in light of this, I just thought it might be interesting to take a look at some of the limitations to null hypothesis significance testing. And it's important to know that this approach to sort of seeing if there's differences between groups is highly sensitive to sample size. So the larger the sample you have, the easier it's going to be to reject your null hypothesis. So if you only had 20 people in your sample, then the power of your test is going to be very low. And so even if there's a relatively large difference between the groups, you may not find a significant difference. However, if you had 500 people that were part of your sample, then your test is highly powered and it's much easier to find a statistically significant difference between the groups. So that's something very important to know. It gives you a little bit of insight about the design of your study in the first place. When the larger the sample size, generally the better it's going to be, because you'll be able to reject your null hypothesis more easily. However, it's also important to know that sample size really does play a role. And null hypothesis significance testing doesn't tell you really what you want to know, and that is how large the effect size is of the treatment. In other words, how big is the real difference between the groups that you're looking at? So if you're comparing one group that received treatment and the other one that didn't, you want to know sort of what's the meaning to the results that you have. So it's possible to get a significant, statistically significant result where you reject a null, but the practical significance about the size of the difference may not be so great. So just as a personal example, I way back when I was teaching 7th grade life science, I started sort of thinking that the kids at the beginning of the alphabet had higher grades than the kids at the end of the alphabet. I don't know if it was an alphabetical seating order or whatever it was, but it was just sort of an anecdotal thing. So I went back and got every student's grades from the 4 core content areas in the entire school. There was about 850 kids, I guess, and I compared the kids from A to M versus those from N to Z. And the ones from A to M had a statistically significantly higher grade point average than the kids at the second half of the alphabet. However, in reality, it was only about 0.01 percentage point. So while there was a statistically significant difference between the groups, the practical significance was not there because it was a very, very, very small fraction of 1 percentage point difference between the groups. So you have to be careful if you only analyze the results of the hypothesis test. Instead, one of the things that you need to report according to APA is the effect size. Okay, so the effect size is really the actual magnitude of your results. So how many, what was the actual difference between them? And there's several ways to report that. And so it really depends on the kind of analysis that you do. So as you work through Yaki, every one of the examples, he's going to talk about the effect size, how to calculate that, and how to report that. And it provides a good model for you to use when you go to do your treatise work. So one of those is Cohen's D. Jacob Cohen developed this, and really it's about the difference. It's a standardized difference in the means between the two groups. So if you're comparing means between two groups using an independent samples t-test, then you would report that as Cohen's D. On the other hand, if you had, let's say, 3 groups that you were comparing the means on and doing an ANOVA analysis, instead of Cohen's D, you would report something called an eta square. And eta square is defined as the percentage of variance explained by the independent variable. So he'll go into more detail about that, and I'm just mentioning that here so that you recognize that there's more than one type of effect size that's